Now, Dunham is a great classification, but like I said, it's based on thin sections. And if you work on reefs, here's a nice example of a reef. You know that some of those reef grains can be extremely large. Here we're looking at a metric grain. And Embry and Cloven in the 70s worked on reef, and they noticed that the Dunham classification was very powerful. They wanted to use it, but it was also not so useful in reefs because everything they looked at was actually much coarser than what is typically classified in the Dunham texture. So they had to come up with an alternative classification that we will explore now, which is known as the Embry and Cloven classification that came out in 1971. So we'll build this classification from the ground up. Know though that it was made for reefs, for people working on reefs that looking at very coarse sediments. And I will preempt things a little bit here and say that we can actually combine this classification with Dunham. So we'll do that later. Let's build this classification from the ground up. What is the first question that comes up? So the first question in this classification is whether you're looking at originally bound together component or a loose sediment, an allochthonous sediment. And if it is an allochthonous sediment, then the next question is, do you have more than 10% of grains that are larger than 2 millimeters? Notice that this limit of 2 millimeter is arbitrary, but it's important because if you don't have more than 10% of grain larger than 2 millimeter, you cannot use this classification. Now, if you do, the next question that comes is whether you are matrix supported or grain supported. In other words, whether grains smaller than 2 millimeter support your framework or whether the grains larger than 2 millimeter support your framework. So if you are matrix supported, so in other words, supported by the grains that are smaller than 2 millimeter, then we talk about a float stone. And you can see that we have those larger than 2 millimeter grain floating into the matrix, hence the term float stone. And here's an example of a float stone. Notice the bar at 1 millimeter here, and I will highlight for you the grains, and you can see clearly that we have more than 10% grains in terms of surface of this thin section that are larger than 2 millimeter, but these grains do not form a framework. They float in the matrix that is smaller than 2 millimeter, and that matrix, by the way, can be micrite, but it can also be just smaller grains. Now, what if we are supported by the grains that are larger than 2 millimeters? Well, then we're looking at what is known as a rudstone, where the large grain form the framework. And here's an example of a rudstone. Again, I'll highlight the grains for you, and you can see these grains basically form the framework of the rock. And in between these grains, we have the smaller matrix that can either be grainy or muddy. Now let's look at another case. If the components are actually bound together at deposition, and this is really one of the reasons this classification was invented. It's to basically look at reefs. Then we have 3 cases that are possible under this classification. Either the organism form a baffle, so a vertical barrier, and then we talk about baffle stones. Here's an example of an ancient baffle stone. This is basically a branching coral, and you can see that these corals form a baffle, so we would talk about a baffle stone in this case. If the organisms are encrusting or binding, so they're much more like encrusting organisms, then we have what is known as a bindstone. And here's an example of a bindstone. This is effectively a algal mat that binds the sediment together. And finally, you can also have organisms that build a rigid framework, so like a full reef, and then we'll talk about a framestone. And here's an example of a framestone. This is an ancient reef that effectively is interconnected and form a framestone. Now, what usually people do, and the classification we will be using as a class, is a combination or an expansion of the Dunham classification with the Embry and Cloven classification. So from now on, when I say we'll use the Dunham classification, I mean the expanded Dunham classification that I'm about to show you. So we start by looking at the component, and we look at whether or not the components are bound together at time of deposition. If the answer is they're not, then the next question is, do we have more or less grains that are larger than 2 millimeters? If the answer is less than 10% of grains are larger than 2 millimeters, then we use our traditional Dunham classification that we've covered before. If we have more than 10% grains larger than 2 millimeters, then we use the terms floatstone and rudstone as introduced before. And of course, if we have autochthonous sediments, so they're not transported, they're bound together at time of deposition, then we use the bafflestone, bindstone, framestone terminology. And we can combine this and have one unified classification that is effectively what Embry and Cloven did. They combined their classification with Dunham to refer to reefs. So when you hear or read about the Dunham classification applied to carbonates, usually it means this expanded Dunham classification. And again, please use this one in this course. I do not mind, if you want to simplify your life, if you just call everything that's bound together at time of deposition as a bound stone. Because in most of the example that we will see in ancient example, it's very difficult to say whether it's a bafflestone, a bindstone, or a framestone, because you need to be able to look at very large areas of the reef, which is not always possible. So I'm perfectly fine if you want to simplify your life and call all the textures that are bound together at time of deposition as boundstone. Of course, if you can use those more specific terms, it's better, but otherwise it doesn't really matter, I think. And again, you can also remember that this classification is very useful because if we can apply it, we have an indication of the hydrodynamism of the environment of deposition, how much energy was present when that rock was formed. And that is key to try to understand the paleo environment of deposition. That and the fossil content are the two things we'll use to do paleo reconstruction of the environment of deposition. Okay, so that brings me to my summary. So what have we learned in this class? Well, we've learned that we will apply the Dunham classification expanded with the Embry and Cloven classification. We learned that these classifications are based on preserved textures at time of deposition. So be careful with this notion because it does mean that sometimes you will need to make an interpretation on the texture that is present in the rock because you will have to strip away any trace of diagenesis. These textures are indicative of the hydrodynamic energy of the environment of deposition, which is why it's so useful. And that gives us an indication of the depositional condition, and we can use this then to build our interpretation in terms of sedimentology or in terms of sequence stratigraphy of the particular system that we are studying. So that's it for now. In the next class, we'll look at another type of classification, which is the classification of porosity.